Hi, everybody. It's me, Dr. Lundholm. We are here looking at section 15.4 on Friday afternoon. It's 5:17. Um, so I hope that this goes well. Kind of feeling the long one coming on because this is, despite as as not intimidating as the multivariable chain rule could be, this stuff actually gets kind of nuts. We're going to do what we can. It's going to be good. All right. So in order to activate your brain cells and get you in the chain rule mode of thinking, I'm going to review the single variable definition of the chain rule, talk a little bit about it, and that's where we'll start. And then we'll get into the multivariable chain rule. It's going to be awesome. Okay. For the chain rule, we have a composition of functions. In the single variable case, we have two, single variable functions, where f is the big function on the outside, g is the intermediate function on the inside, and your independent variable is x. And remember, the chain rule goes like, if when you're taking the derivative of this whole composition with respect to x, you take the derivative of the outside function with the intermediate function still hanging out, filling inside, multiply it times the derivative of the inside function. And the reason for this is maybe best explained if we look at some number lines. Imagine that this is, yes, the x number line. Here's a g number line, and here's the f number line. So input variable, intermediate, and dependent variable, dependent variable out here. When we're taking derivatives, and at this point, you might want to look down here. These are two different ways of expressing the same thing. But when we're thinking about a derivative, we're trying to find, when we nudge x a little bit by some nudge dx, what resulting change does that make the overall function f in the end, the biggest function on the outside? The idea is you nudge x a little bit, that causes nudge in g, and then resulting nudge will cause a nudge in f. When you put in the value of g into the function f, that's going to cause another nudge. And what we're doing right here is we're multiplying together two rates of change, and it's the rate of change between dg and dx, which is, the derivative of g with respect to x. It's g prime of x. So this part is this rate of change. It's the speed at which g changes with respect to a change in x. This one is the speed in which f changes with respect to a change in g. And so multiplying those two rates together gives us the overall rate of change with df and dx in the end. So that's the end result. That's what we were looking for. That's a single variable chain rule. And again, two different ways of saying the same thing. This is df dx. This is df dg. This is dg dx. Same dealio. Okay, so with that single variable chain rule out of the way, move on to the multivariable one. Because now we get to introduce partial derivatives, and it's going to be great. It's not going to make it more complicated. Here we have y, which is some function of u and v. And u is a function of x, and v is a function of x. The hierarchy of things going on here, if you want to view it, let me make sure I'm consistent with things that I've done before. Okay, we'll start from the bottom. And if we wanted to build this up, yeah, we can use black, that's fine. X is our independent variable. Think of that as like our input. So we've kind of almost got a single variable input, but what's happening is that X is getting input to functions that we're calling G and H here. But those correspond to some intermediate variables U and V. And then U and V both go into a multivariable function called F. And I guess because we're giving everything two names here, that dependent variable is called Y. I would call these ones intermediate. And one of the things that I haven't necessarily emphasized as much the last time that I've taught this course, but I feel like I should emphasize right now, is that you can almost look at U and V, these functions, as parametric equations, like the vector valued functions that we've looked at previously. Whereas you might even want to start thinking of a vector that looks like G of X, H of X, where G is the U component and H is the V component. Because actually this is going to be important. It'll be a good way of viewing the chain rule as a dot product later on. You can see in this definition, we have kind of a dot product going on because we've got two things being multiplied together here and two things being multiplied together here, and there's an addition sign in between them. So this could be like a dot product of two things, two component vector dotted with a two component vector. This could be the result. It actually will be the result of a dot product. So this is a good way to kind of view those intermediate variables. We've got one parameter going in. Most of the time that we've seen this before, this letter would be T. We viewed that as the input variable for these kind of things. But yeah, each one of those are single variable functions. And I guess I could, that this is G of X and this is H of X. This one is F of, UV. So these two functions are single variable functions. This is a multivariable function, and sometime soon this should update. While we're waiting on that update, in order to make sense, to give you an intuition of what's going on here with the multivariable chain rule, I tried to make a relatable example. So imagine, if you will, you are a student who is taking both Calculus 3 and Physics. I know that not all of you are, but imagine you're taking Calc 3 and Physics, and what we're going to do is calculate your GPA, and specifically the rate of change of your GPA. We're going to do that with respect to the number of hours you study per week. So the way that I want you to view this is that we have one independent variable, X, which is the number of hours that you study per week. We're going to have two little functions of X called V and H, and those are more about like your grades in Calculus 3 or your grade in Physics, for whatever. So you can imagine that your grade could be a function of the amount of hours that you study per week. But then you would maybe want to think about your GPA, which incorporates multiple courses. So your GPA is a function of your grade in calculus and your grade in, say, physics. So we can look at the rate of change of your GPA but we have to go through a couple of layers here. We have to, the next layer is grades. Those grades are affected by how much hours you study. So one way to, put some labels and understand what each one of these is, df(x), where, f is the big function on the outside. F is a function of g and h. That would be the rate of change of your GPA with respect to the amount of hours that you studied. So this is the rate of change that we want to get in the end. In order to get that, we need to multiply some rates of change together, which actually it's going to be a dot product. We're going to look at that soon. But yeah, think about for calculus 3, what you would need to do is figure out the rate of change of how many hours you study affects your grade, and then you would be multiplying that times the rate of change of how your grade changes, how that changes your overall GPA. And similarly for the other class, how a change to the number of hours you study affects a change in your grade, and how that change in your grade affects the change in the overall GPA. So yeah, maybe that helps, maybe it doesn't. If you still need to talk more, maybe pause and you can think about things amongst yourselves and with Allie. We're going to get into an example really soon, and hopefully that will clear some stuff up, hopefully. All right, so this is case 1. This is actually the easier part, where we actually have some single variable functions. Next one, we're going to have multivariable functions in the multivariable function. It's going to be great. Right now, let's take a look at example 1. And here again, x is our input variable. You might want to view these intermediate functions u and v as a vector. So if I was going to make like a vector function, we could even call it, I don't know, r of x, because x is our input variable, where x squared is like your u component, and x cubed minus 1 is your v component. You might want to keep this in the back of your mind. I mean, actually, I'll show you. Once we look at this, I'll show you the dot product stuff, because I keep hinting at it and I'm not showing you yet. Anyways, keep this in the back of your mind. The idea here is that we could find the result of the multivariable chain rule by looking at this multivariable function and taking some partial derivatives, one of them with respect to u, the other one with respect to v. If we take the partial derivative of y with respect to u, and remember, we're treating v like a constant, we would do the power rule on u, so we get 3u squared, and v would just be v squared. So this is the partial derivative, 3u squared times u, or v squared. Multiplying it by du dx, here we're looking at this function and we're taking the derivative of u with respect to x, which just is 2x. And very similarly here, this is the partial derivative of y with respect to v. Power rule gives us 2u cubed times v. And over here, for finding the normal derivative of v with respect to x, again, power rule 3x squared is there. To finally get everything in terms of just your independent variable x, you can go ahead and make those substitutions after you've taken the derivative. And that's pretty nice. You get something good there. All right, I'm going to move that up and we're going to do the dot product version, because the dot product version of this, I feel like, is unifying, and it will be extendable when we get to crazier and crazier things. It's going to be kind of a guidepost for us. So let's do this problem over. I move this part up here. We've got, u and v, treat it like a vector valued function. Let's take the derivative of that like we normally would have in that chapter. So I'll do this in orange. I don't know why, but and we just take the derivative component wise, 2x and x cubed minus 1. So finding that derivative is not so bad. The other thing that we will need for this multivariable chain rule when we're finding dy dx is something called the gradient. The gradient is notated oftentimes like this, and actually I'm gonna write y here for our variable because y is the one that we're given. We could treat y as, we've got y of a function. It's a function of u and v. Anyways, the gradient is going to be a vector full of the partial derivatives of y. And we'll be multiplying that gradient times like this vector valued derivative that we found, not of t, of x. I'm so used to writing r of t. This one is r of x. Anyways, the idea is we're going to have two vectors here. We're going to have the partial derivative with respect to u and the partial derivative with respect to v in a vector, and we dot that with the derivatives of u and v over here. And so, notice if we actually compute those partial derivatives like we did before, partial derivative of u was 3u squared v squared, and the partial derivative of y with respect to v was 2u cubed times v and now you have, I don't know, this whole multiplication and addition. All of that multiplication and addition is encapsulated in one dot product. And so this may or may not make more sense to you. Because now the multiplication and division are taken care of. I know I need to multiply the first two components together and add that times the product of the second components. And we would get, the same exact thing as we got at this stage here. And to get into why that is the case, that dot product ends up being the value of this, kind of the total derivative of the biggest function that we have. We will see that, I think, in the next example. I've got a cool graph. It's going to be great. But no GeoGebra on this one. This one, we're just keeping simple. Okay. If you have any questions, go ahead and pause it. I'm moving on to the next one. Example number 2. Okay, good grief. We've got a lot of stuff here. This time we are determining the rate of change with respect to t of the function f of xy, which is equal to xy. So that's our multivariable function this time, along the Lissajous curve described parametrically by x equals sine of 2t and y equals cosine of 3t. Okay, so this is the Liouville curve, and that's just graphed in the XY plane for right now. But it's a parametric curve. Okay, we're going to calculate the derivative of, f with respect to t. So we've got the outside function as our multivariable function, and we're inputting a couple intermediate variables, but t is really our independent input variable. So yeah, we can calculate, I guess we could calculate this derivative at specific points, but at this point, I still want to focus on taking the derivative generally. So, this is what this looks like. We're finding dft, multivariable chain rule again. Notice that for each one of these sections, the intermediate variable kind of fades away if you cancel out across this diagonal, and you're just left with df dt and df dt, or partial f dt and partial f dt. But yeah, it's not completely wrong to think about it that way. But we need x components contribution, and we need y components contribution to get the total thing. And so, yeah, you can again view this as the dot product of the gradient vector, and the gradient vector in this case is the partial derivatives with respect to x and y. So if we take the partial derivative of f with respect to x, we just have y. And if we take the partial derivative of f with respect to y, we'd just be left with x. Again, like that's the power rule. It's just because, for that last one, when we're taking the derivative with the partial derivative with respect to y, x is just a constant that's coming along for the ride. So yeah, we just get x here. And then this one, this is the tangent vector to the path that's being traced out in 2 dimensions. So yeah, I mean, you might want to think about, as you're going along, r prime of t would look like a tangent vector along the curve at some certain point. And finding that, we would take the derivative of sine of t, or sine of 2t in the x component, and get 2 cosine of 2t. And in the y component, we would have -3 sine of 3t when we take that derivative. And yeah, so notice, yeah, the dot product matches up with the stuff that we would see here. So that's all good. But yeah, the thing that's not, the vector that I didn't draw on this graph yet is the gradient vector. And the gradient vector is going to be dependent on the underlying multivariable function. It's going to point in the direction of steepest ascent. And so really soon, we're going to look at this in 3 dimensions. The gradient vector is a 2-dimensional vector, so it does kind of belong in this space. I don't necessarily know which direction to put it here, although, okay, this is x times y. And so, okay, this is the point that is a little bit less than 1 in the x direction and almost 0 in the y direction. I need to make that vector, but according to the very small number in the x direction and the relatively large number in the y direction. So I think okay. It's still going to go this way. All right, so if I was going to make a gradient vector here, yeah, we want this to be the vector y comma x, and starting from this point, it looks like I'm trying to go, the y value for this point is small, so I only go to the right a little bit, but the x value for this point is bigger, so I go up quite a bit more. It's going to make more sense when we actually look at this in 3D, but the gradient vector and this tangent vector are actually two-dimensional vectors that you could visualize in like a two-dimensional plane. Let's go to GeoGebra, although I don't know what okay, here. Now let's go to GeoGebra. Oh, I already have this open. Let's pull it up here. All right. Let's get rid of this one for now. So this is actually the tangent vector and gradient vector if we're looking down at this at a two-dimensional plane. So I'll play this real quick, and you can see the red tangent vector is just going straight along the path, and it gets longer when those t values move the point around the curve faster. And the green vector is the gradient vector, and that one's always pointing in the direction of steepest ascent of this function xy that's underlying everything. So if we pay this off and look at it in 3 dimensions, this is the curve that you might expect happening. Yeah, originally when we were given this problem, come on. Here we go. We're on the function xy, but x is given by sine of 2t and y is given by cosine of 3t. So this is defining a path that we're going to travel around this function, is maybe the way that you want to think about it. Come on, let me get back. Okay. And so what's actually happening is we're finding the rate of change along this function. We're still finding like a rate of change of z values, if that makes sense. We're finding the rate of change of the function. So the rate of change that we're finding, it really is a z value, but we're able to find it by taking the dot product of the tangent vector along this curve and the gradient vector, which points in the direction of steepest ascent. Notice that, this is going up in this direction, gradient's pointing that way. If we let it go around a little bit more, I want to hit it. There we go. If we let it get down to this bottom point, notice the gradient is pointing towards the origin because that would be the direction of steepest ascent from this point. Maybe, there we go. I got point P, that's good. And yeah, if you look down on it, the tangent vector is tangent to that curve. So yeah, taking the dot product, for whatever reason, my gradient vector is labeled U, and my kind of R of t vector, the vector that's going along this space curve in 2 dimensions is called J. But when you take the dot product, notice that we're pointing in a similar direction this time, so we get a positive derivative. And notice that if we were down here and continuing along this path, we would be going up. So getting a positive derivative there makes sense. To make a connection to derivatives that we've done in the past, let me get rid of the gradient vector and the 2-dimensional tangent vector. And what if we just make a three-dimensional tangent vector. Now, we've seen three-dimensional tangent vectors before, and look how it goes up and down. It just goes along the space curve, even accounting for the z direction. So that's super cool. How did I get that? Well, if you go back to, our original function, this gives a z value in terms of x and y. So what I was able to do is make a curve all in terms of t, where I put in the sine of 2t in for x, cosine of 3t in for y, and then their product in for z, and that gives me the curve that zooms around on the surface of this thing. And so creating the tangent vector from there is not so bad. We've just got basically a vector that's x, y, and then x times y for the z value. So we can have this three-dimensional tangent vector that zooms around the curve, and that's really cool. But how does this three-dimensional tangent vector relate to the two-dimensional tangent vector that we were looking at before and the gradient vector that's completely new today, but it points in the direction of steepest descent. And remember, the gradient is the partial derivative with respect to x, comma, the partial derivative with respect to y. Okay, so the question is, how does this three-dimensional tangent vector relate to the two-dimensional vectors that we've looked at with the multivariable chain rule? Well, remember, we take the dot product of these two, the two-dimensional versions, to get the derivative, which in this case is negative 1.9. Notice that our tangent vector is heading in a pretty opposite direction to our gradient vector. And so having a negative dot product makes a lot of sense, right? They're almost completely polar opposites. So negative dot product makes sense. That means that we're going down in the z direction, and our three-dimensional tangent vector relates to that perfectly, because remember, the dot product down here is negative 1.9. Well, what's the z value of our vector here? Negative 1.9 is the z component of our tangent vector. So the z component of the three-dimensional tangent vector is the dot product between the gradient vector and the two-dimensional tangent vector. I don't think that I've ever been able to describe things that succinctly before, anytime I've taught this class, but it's super cool. We're taking the dot product between the 2D tangent vector and the gradient, and that dot product is the same as the z component of the three-dimensional tangent vector. And because fundamentally what we're doing when we take the chain rule, come on, this is not behaving. I want to go back to OneNote. We're finding a rate of change with respect to a z value. F of xy is a z value. So that, yeah, that's what we're finding. I think that's super cool. Hopefully this dot product thing will continue to be useful to us as we move along. Yeah, what time is it? Ooh, 5:51. All right, let's keep going. Now we look and we get a new theorem for the chain rule, case number 2. The difference now is that u and v, our intermediate functions, are now multivariable functions themselves. So we've got multivariable functions on multivariable functions. This is the tree diagram that you could, kind of look at, but x and y are our input variables. They're independent variables. U and v are our intermediate variables, and then z is our dependent variable at the end, the thing that we're trying to get overall. But notice that since we don't have any single variable functions here, everything in the multivariable chain rule is all partial derivatives because we're doing, derivatives of multivariable functions the entire time. And notice that instead of just having one derivative, like here we were able to just find df dt, or here we were able to just find dy dx, just one derivative. Now in this case, where we've got multivariable functions going into multivariable functions, we've got a partial derivative with respect to x, one of our input variables, and another partial derivative with respect to y, our other input variable. So here we've got partial derivatives which are themselves chain rules. Okay. Example number 3. Let's take a look at this. Z, our big function, is made up of u and v, and then u and v are our intermediate functions. Those are made up of x and y. So, same diagram here as what was going on here. Again, we're lining up chain rules, or lining up these derivatives so that if you were to cancel partial u and partial u, or partial v and partial v, you still get the same thing as what you're hoping to get. Here we're trying to find partial z, partial x. So we get partial z and partial x, and partial z and partial x. We want to make sure that that happens. And again, we could do this with dot products. It's just the dot products will look a little bit different this time. So yeah, while you're looking at that, if you've got any questions, go ahead and make that known. Let me think about the dot product stuff here, because the gradient of z is going to be a thing. The gradient of z will just be a vector that looks like, partial derivative of z with respect to u would be, the 2v thing is just going to be treated like a constant. So one way that it might be nicer to view z, z could be rewritten as e to the u times e to the 2v. I think that'll make things clearer. That's just a property of exponents, right? But when we're doing the partial derivative with respect to u, it means that we're taking the derivative of this with respect to u, which is just e to the u, and this just comes along for the ride. So it's still going to be the same thing here. It's going to be e to the u plus 2v for that partial derivative of z with respect to u. Then, if we take the partial derivative of z with respect to v, again, I think looking at this way is productive. We would have 2 coming out, using the single variable chain rule. But yeah, we'd have 2 coming out front, and this would all still be there. So I would say we have 2 e to the u plus 2v for the gradient of z. So that one we would use in both of these products. But in order to get, the other one, maybe we call the vector version of the u equation and the v equation, maybe we call it r. But what we would be trying to find then is the partial derivative of r with respect to x. So we would go component wise, and take the partial derivative of u with respect to x, which would be 3x squared times y. And then we would take the partial derivative of v with respect to x, which would just be -1. So notice that the thing that we get down here is the dot product of those two vectors. For the other one, we would want to do the partial derivative of r with respect to y. Now taking with respect to y, we just have x cubed for that first part, and taking the partial derivative of v with respect to y, we'd have 2 times y. And notice that's what shows up, down here for this dot product. Again, it would be the dot product between, well, here, I'll do that. This is the dot product between the gradient of z and the partial derivative with respect to y. And this one is the gradient of z dotted with the partial derivative with respect to x. This is fun. Multivariable chain rule. All right, we have no time to sit around. I mean, if you want to ask some questions, go for it. We got to keep going. All right, this is just what we just did, but on steroids, where we're allowed to use however many variables that we want to for independent variables and however many variables we want for intermediate variables. So this is just ginormous. Like, yeah, we've got n intermediate variables here. We have m independent variables going into those functions. And yes, for each one of the individual partial derivatives with respect to one of the given input variables, you do a whole dot product, just like we did, this dot product to get this, or this dot product to get this. You're taking the gradient of the big multivariable function, and you're taking the dot product with kind of the vector valued function that's a partial derivative of some intermediate thing. So partial derivative of the intermediate functions, a vector full of those. Yeah, and that one's, that's pretty crazy. Don't worry, we're gonna keep it mainly to, working with 2 or 3 variables at each stage. We're not gonna get into an indeterminate number of variables. Okay. For example, number 4, here we've got w that is a function of x, y, and z. So here we've got 3. And the x is a function of s and t, and so is y, and so is z. So if we wanted to make a diagram of this one, s and t are our input variables. S and t are going to go into a function called x, and s and t are going to go into a function called y, and s and t are going to go into a function called z. And then x, y, and z are all going to go into a function called w. That's the hierarchy here. So we want to determine these chain rules, and maybe you want to pause and see if you can try this out yourself, to give yourself a head start and see if you come up with the same thing I do. Hopefully we come up with the same thing. I'm gonna do, I'm gonna do the dot product version of this. I kind of like that version, and I don't like writing all the partial symbols and all that. Anyways, okay, gradient of w. Okay, actually, hold on. To find WS. And then we're going to do WT down here. But in order to find W sub S, the partial derivative of W with respect to S, we're taking the gradient of W and dotting that with, I'm going to call it R, but this will be R, well, not prime, because it's going to be a partial derivative. It's going to be, yeah, the partial derivative with respect to S. Sorry. Then we're going to do the gradient of W times the partial derivative with respect to T for this one. All right. Gradient of W. It's going to be a vector full of partial derivatives. So that vector full of partial derivatives will be the partial derivative with respect to X in the first component, partial derivative with respect to Y in the second component, and partial derivative with respect to Z in the third component of this 3-component vector. Okay, we can do this. Taking the partial derivative of this whole thing with respect to X, we're just going to be left with 2y cubed for that first part. And actually, yeah. All right, 2y cubed. Here we would have 2xz, so plus 2xz. And I need to erase this because I'm going to run out of room. And then no x's are found over here. So this is just being treated like a constant. It falls by the wayside. So we found the partial derivative of W with respect to X. Here's where we find the partial derivative of W with respect to Y. Here we get 6xy squared according to the power rule. There's no y's in the middle term here, and there's one y over here, so we just get minus z squared. Then we're finding the partial derivative of W with respect to Z. No z's here. There's one z here, so we get an x squared for that term, and so minus 2yz for that last term. Woo! Okay. There we found the gradient of W, and this we can actually just copy and paste. Let me see. Let me be really fancy. Oh, geez, that was horrible. We got it. Copy and paste. Nice. That way I don't have to write it down another time. This again, that's the gradient of W. Now we're going to be taking the dot product of this gradient vector with here we're going to find R sub S. And so if I go up here, let's actually just make our vector R of S and T and write that as a vector valued function. So we've got S minus T and S squared plus T squared and S times T over here. Now we take the partial derivative of each one of these components and put them in a vector. So partial derivative with respect to S here would just be 1. Partial derivative of with respect to S here would be 2S. And a partial derivative with respect to S here would just be T, because remember, T is acting like a constant. No, T. Okay. So we have our dot product to do, and just taking the dot product would give us that partial derivative of stuff. And yeah, if you want to be really complete after having done this partial or this dot product, you could substitute in s minus t in for x, s squared plus t squared in for y everywhere you see it. And yeah. Yeah, s times t in for z. And then you truly would have a function of s and t like you were hoping to have for your partial derivative of w with respect to s. So yeah, you can do that. For this one, we would take the partial derivative. This one will be r of t. We're going to take all the partial derivatives with respect to t. So the first component here would be -1. The second component would be t. And the last one would just be s. And again, taking that dot product will give you the multivariable chain rule, the derivative, the partial derivative of w with respect to t. Lovely. I'm going to leave it like that because I don't want to do those dot products right now. It is 6:08. Grief. Sorry. Example number 5. Lovely. I even just implore the book on this one because, yeah, there's a lot to do. Here, we're looking at second order partial derivatives. Isn't that nice? So after realizing that you've got a multivariable function that's taking in multivariable functions as inputs, not only do we need to find the first derivatives, but we want to find the second order partial derivatives. So the idea would be, we could find the single partial derivatives using the chain rule, like we've done previously. One thing to watch out for here is they don't give us a formula for z. So when we have partial z, partial x, I'm just writing the partial derivative of z with respect to x. That just has to stay a mystery because we don't know a formula for that z. And so, same thing over here. There's partial derivative with respect to u. Here's the partial derivative with respect to v, but notice, we don't have enough information to turn these into u's and v's, so that just has to stay the way they are. Good grief. So in order to do this, we would take the partial derivative of everything that we see here with respect to u. Again, so this is the partial derivative with respect to u. We're doubling that up and we're doing it again. In order to do that, we're treating z like each of these partial derivatives, z sub x and z sub y, as unknown functions of u and v, because the u and v are our input variables. So this whole thing is kind of a mess. For the first part, we don't, well, actually, yeah, for the first part, we do a product rule. Yeah, sorry for hesitating there, but we do a product rule because we have a function of u here times another function of u because we're treating the partial derivative with respect to x as a function of u and v. So these first two parts, this is product rule. Yeah. And you don't need to do the product rule on the second part because v is just like a constant, but this partial derivative with respect to y, we're treating it as a function of u and v. So you do need to do the chain rule on that one. So v just comes along for the ride. Eventually, we're going to do the chain rule on this part, but right now we're just writing it as the derivative, the partial derivative with respect to u of this thing. Yeah, so kind of a weird notation would make it this like z sub y u, but you don't really want to mix intermediate variables and the independent variables. We're gonna change everything into the independent variables towards the end here. But yeah, as part of this product rule, we need to take the partial derivative with respect to u of this z sub x, which itself is a function of u and v. And so there's a chain rule that goes along with that. And this is the chain rule that you see. Yeah, this, oh, I meant to change colors. This whole thing is the multivariable chain rule that we see here. And this is the multivariable chain rule that we see there. Lovely. Yeah, so this one's nuts. Honestly, am I going to have you take second order partial derivatives of this? Probably not. It's good for you to, see it at least once. This, yeah, okay. Each one of the blue one and the purple one, those are multivariable chain rules. And after that, it is kind of tidying up. Here we have partial x for z. Here we've got partial x partial y, so that's why that one's here. Yeah. Lovely. So these things get reduced down. And finally, you get something in terms of partial derivatives with respect to x and y and your variables u and v, your intermediate variables, because you don't really have a way to change those into x and y's because we're never for z. Anyways, I hope that was fun. Honestly, I had more fun on the other ones. The last major topic, I know, there's another one, right? The last major topic in this section is implicit differentiation via the chain rule. That's just what we needed, right? Instead of being given a nice formula for a dependent variable, now we're going to do implicit differentiation and make our lives easier. Rather than doing a bunch of multivariable chain rules, as we just would maybe try tackling this one. I mean, actually, finding dy dx here is something that we probably could do with the implicit differentiation stuff that we've done so far. But there's a cool relationship here that allows you to express the derivative as a ratio of two partial derivatives. And the idea is you start off with, you get everything with all of the variables onto the left-hand side and that make it equal to 0. So when we start off with this, we subtract sine of xy from both sides so that we can make a big old function, x cubed minus y squared minus sine of xy. So we're treating everything like it's a multivariable function of the variables that we have. When you have it like that, though, when you're taking partial derivatives, notice that, the right-hand side will still just be 0. And when you apply the multivariable chain rule, this is the kind of thing that you would get on the left-hand side. Now, if we zoom in on this multivariable function, or this multivariable chain rule, the dx over dx is trying to be sneaky. It was hiding there. That's just going to be a 1. And so essentially what you have is this partial derivative plus this partial derivative times dy dx, and you're able to solve for dy dx because, this one's just the partial derivative with respect to y. This one's just the partial derivative with respect to x. And you're able to solve this equation and isolate dy dx. So this feels like a shortcut to some extent. And that might be a breath of fresh air at this stage, where if you want to find dy dx, you make a big multivariable function of x and y by getting everything onto one side, and then you take two partial derivatives, one with respect to x and one with respect to y, and you put them in a ratio of each other, and don't forget the minus sign. But yeah, this is the implicit function theorem. Ooh. Super cool. And again, here's a version where you've got partial derivatives, because this was one where we had, I don't know, just one multivariable function. So yeah, you had partial derivatives. Sorry, but the overall idea here is that we were treating y as a function of x. Here we're looking at z as a function of x and y. And so yeah, we get more partial derivatives. Guys, honestly, this is cool. I might throw one of these at you. I mean, there'll be something on the homework probably. The main idea though is to get everything onto one side and then take partial derivatives respectively for the top and the bottom. I'm not gonna, throw something crazy at you on your next test. Well, it's cool to look through the details of this. Right now, these are formulas that you can go back and utilize. I don't feel like going through them at this point, and it is 6:20. Hopefully this is not too crazy long. It might be a little bit too long. I will see you next day. All right. Bye. I'm done. Oh.